Welcome back to the deep dive. Today we're jumping into the OEIS again, focusing on something especially for you number theory students out there. We're looking at sequence A000318.
Ah, yes, A000318. It's known as the generalized tangent numbers D4N.
And the first thing you notice, the initial terms are 4, then 128, then a huge jump to 16384.
Exactly. That growth is, well, it's incredibly rapid. It makes you immediately ask, what's driving that? What's the underlying math?
It really is striking. And this isn't just some obscure sequence, right? It has some history.
Oh, absolutely. It was included in N.J. Sloan's original A Handbook of Integer Sequences back in 1973.
Wow, okay.
And then again, in the Encyclopedia of Integer Sequences in 1995, its presence there really signals its foundational importance. It's not just a curiosity.
So it's recognized as significant. Now, you mentioned a formula connecting it to another sequence.
Yes, there's an explicit formula, AN equals 2 4N2 times A000182.
A000182. Those are the generalized Euler numbers, or second numbers, right?
Precisely. And for you, the student, seeing that formula is a big clue. It hints that maybe there's a combinatorial link, that the things counted by A000182 are related to A000318, just scaled differently.
Interesting. So studying one potentially sheds light on the other.
Exactly. It reveals a structural relationship, something deeper than just the numbers matching up.
Okay, so we've got the rapid growth, the history, this connection via the formula. But what about the name? Generalized tangent numbers. Where does the tangent part come in?
Ah, good question. That really gets to the analytical side. Peter Lushny pointed out that these numbers, AN, are coefficients.
Coefficients of what?
They come from the Maclaurin series expansion of the function sec4 x sin 4x.
Okay, second times sine, sec of 4x is 1 cos 4x. So sin 4x, 4x, that's just tan 4x.
You got it. It simplifies beautifully to tan 4x. So the sequence terms are literally tied to the series expansion of the tangent function, specifically tan 4x.
That makes the name make perfect sense.
Yeah.
Now, I also saw a note from Thomas Baruchel about the generating function, something about continued fractions.
Yes, that's another fascinating layer. The generating function for 0000318, remember, that's the power series whose coefficients are our sequence AN.
Right, it sort of encodes the sequence into a function.
Exactly. And this particular generating function can be expressed as a continued fraction. That's quite significant.
Why is the continued fraction form so important here?
Well, continued fractions are a powerful way to represent functions, often revealing deeper structural properties, and even more, the convergence of this specific continued fraction, the rational numbers you get by truncating the fraction.
Yeah.
They are actually Padé approximants of the Maclaurin series.
Padé approximants, I've heard the term, but maybe a quick refresher. What's the power of that connection?
Sure. Think of Padé approximants as the best possible rational function approximations for a given function near a certain point. They often converge much faster or in wider regions than simple Taylor series truncations.
Okay, so they're really good approximations.
Extremely good, using rational functions. The fact that the convergents are these Padé approximants links the discrete sequence through its generating function's continued fraction directly to powerful methods in approximation theory and analysis. It bridges the discrete and the continuous.
So pulling this all together, sequence A000318, these generalized tangent numbers, they start as simple integers, but they connect outwards.
That's the beauty of it. You start with 4, 128, 16384. But you quickly find links to history, to other important sequences like the Euler numbers, to analytical functions like tan 4x, and even to advanced concepts like continued fractions and Padé approximants.
It really serves as a bridge between different mathematical ideas.
Precisely. And that's the aha moment for you, listening as a number theory student. Seeing how a sequence of whole numbers can encapsulate all this complex structure, generating functions, series expansions, sophisticated approximations, it shows how interconnected maths really is.
It definitely makes you appreciate what can be hidden inside a simple list of numbers. Which brings us to a final thought.
Ah, yes.
The OEIS entry keywords, this sequence, A000318, as non for non-negative and easy.
Easy, yes.
After digging into explicit formulas linking sequences, Maclaurin series for trig functions, continued fractions, Padé approximants, what does easy even mean in this context?
It's a provocative point, isn't it? It makes you wonder, how many other sequences tagged as easy in the OEIS are hiding just as much depth, just as many surprising connections, waiting for someone like you to explore?
Something to think about. That's all the time we have for this deep dive. Thanks for joining us.